Hi, everybody. This is lecture for lesson number 2. What we're going to talk about is, at first, particles moving in a magnetic field. Now, last day I told you that there was an equation, F is equal to BQV. B stands for magnetic field strength. It's actually beta. Q, charge on the particle, and V is the velocity particle. And that equation tells you that particles that are moving in a magnetic field will experience a force. Now that's pretty cool. They have to be moving. A stationary particle in a magnetic field experiences no force, but a moving one does. That's weird, or at least I find that interesting. Now, we also learned that there was a right-hand motor rule, which was this. The fingers were magnetic field lines. The thumb was the direction of the velocity of the positive particle motion, and the palm indicated direction on which the object was going to get pushed. Okay, which the particle would get pushed. So BQV, right-hand rule. Now, I'm going to show you a situation that's fairly common when a particle enters a fairly large magnetic field. All right, let's look at that. That's in the notes and looks like, whoops, doesn't look like that. That's a wrong set of notes. There it is. There it is. Okay, so particles enter a magnetic field. What you can see here is these little X's. See these little X's? There's no circle around them. If there were a circle around them, they would mean they were a wire carrying current away from you. But the little X without the circle represents a magnetic field away from you. So what we have is a magnetic field. If you're looking into your page like I am, you have a magnetic field that's going away from you like this. And the right-hand rule, my fingers are the magnetic field line, so they're going to point away from me like this. Now you'll notice that there is a particle moving in from the side. It's an electron. And if an electron moves this way, then a proton would move the other way. So put your thumb in that opposite direction, your fingers into the field, and you can see when the particle here enters the field, it's coming along, then right now it enters the field, okay? You can see that the force initially pushes down on the particle. That causes it to change its direction, and it changes its direction, that changes the force, right? So it pushes it down, it starts moving down. Now it's going this way. Let's watch it come in again right here. So here comes the particle. It enters, there's a downward force, but then the velocity changes direction, so the force changes direction. And that causes the particle to move in a circular path. Ooh, circular path. We know something mathematically about circular paths. Okay, so anything traveling in a circular path must have a net force towards the center. That's what you know from the circular motion unit. So here it is, the net force towards the center is this one right here. It's the magnetic force acting on a moving particle. We have an equation for that, it's BQV. So Fc is equal to force supporting minus forces opposed. Well, there are no opposing. There's only that one supporting force, so that's Fb. Replace that with BQV and replace Fc with MAC. AC then gets replaced with V squared over R, and we have this equation. BQV is equal to M onto V squared over R. I could calculate any of the values here based on this situation. Because look, it enters into a circular path. Now, in this particular example, though, the particle exits the field before completing the circle, right? It enters the field at the halfway point, or exits the field, sorry, at the halfway point. If the field is strong enough, that won't happen. The particle will come flying in at high speed, enter the field, and start going around in a circular path, and then be trapped in that circular motion. You can literally trap these moving particles in a circular motion inside a magnetic field. And that's exactly what happens at the poles of our Earth. If you think of our Earth as a giant bar magnet with magnetic field coming out one end and in the other end, just like it does on a bar magnet, then particles traveling through space, for example, particles released in the sun, charged particles, flying at high speeds through space, can be trapped inside the magnetic field of our Earth. And they do. Cool thing is, under certain circumstances, that little particle enters into our magnetic field, gets trapped, and is caught in this little circular path. Eventually, that little particle loses energy, slows down in that circular path, releases energy in the form of light, and changes its circular radius, the radius of the circular path, right? Which is R in this equation. Now, when it does lose that little bit of light, that energy in the form of light, and if you have billions upon billions of particles doing this at the same time, what you have is northern lights, aurora borealis. Aurora borealis is based on particles traveling through space caught in our magnetic field, changing the radius of their circular path in that magnetic field, thus releasing some energy in the form of photons of light, and the amount of energy depends on the amount of color of light. Cool. That's how the aurora borealis works. Okay. All right, so let's go on. So here's an example of a question. This is describe the path of an electron. When they're asked to describe the path of an electron, and if that particle's path is circular, the way to describe it is to tell the radius. That is the way to describe a circular path with radius of whatever. So describe the path of an electron travels through a 0.1 Tesla magnetic field if the electron has a velocity of 2 × 10⁻⁷ meters per second. All right, so here we are. We start off with FB equals FC, no problem. BQV equals MAC, no problem. AC we replace with V squared over R because we're looking for R. We know it's a magnetic field of 0.1 Teslas because the question gave it, so that goes in here. We know the charge on a electron, that goes here. This velocity got canceled with one of the two velocities here. So I canceled this with one of those two, leaving me with only one here. That's the mass of the electron, and that's the radius of the circular path. Turns out it's 1.1 × 10⁻³ meters, or 1.1 thousandths of a meter. Right, I guess that's 1.1 millimeters. Very small circle, okay? But it's a small particle, and it's traveling at extreme speeds. Okay, so particles moving in a magnetic field. They can be captured into circular paths based on the fact that as soon as they enter the field, the magnetic force on it causes it to change direction. When the direction changes, the direction of the force changes with it, and that causes it to be pointing towards the center of a circular path. All right, now, one more thing we're going to cover in this lecture. Oh, two more things. Right. Here we have a particle passing through a magnetic field, but it's not passing through at right angles. So remember the right-hand rule? The magnetic field lines here and the particle velocity here are at 90 degrees to one another. Now, no matter how you orient your hand, you cannot orient your hand such that this changes unless you do that, and that's not the way to do it, right? So when a particle enters a magnetic field like this, it is doing two things. It's going across the field lines at an angle. What it's really doing is it's traveling horizontally somewhat and vertically somewhat in the diagram. And it's the vertical path going across the field lines that causes the force to act, right? Because the field lines and the velocity of the particle have to be at 90 degrees to each other. So when we get questions like this, where the particle is not traveling directly 90 degrees to the field lines, we have to figure out how much velocity is traveling directly 90 degrees to field lines. So instead of F equals BQV, we have F is equals BQ, and then it's V sine theta to find the vertical component of the velocity that travels perpendicular to the field lines. That's all that this slide is telling you. The particle must travel perpendicular to the field lines. If it doesn't, you have to figure out how fast it is traveling perpendicular to the field lines. Okay, I'll give you a question in the class starter on the next lesson to make sure you remember that. All right, last thing for today, this is for sure, is the magnetic field produced by a solenoid. So solenoid, if you remember, was just a bunch of loops wrapped many, many times. So here you can see many coils, loops. They're also called armatures. A whole bunch of loops together is called an armature. So they have a whole bunch of different names: coils, loops, armatures. I'm trying to think if there's any more. There might be a few others. Anyways, a bunch of loops of a single wire. You pass electricity through it, and it makes a very strong magnetic field, especially down the center or through the hole of the solenoid. Unfortunately, I'm not at school, so I can't actually show you what a solenoid is. I have one at school, that actual real solenoid. And we can generate a very strong magnetic field with that solenoid. In any case, this diagram here shows you that solenoids have magnetic fields with direction, and that direction is just like a bar magnet. So in this solenoid, this end here, this is the north end, because magnetic field lines run north to south on the outside of a bar magnet and on the outside of a solenoid. On the inside of a bar magnet or the inside of a solenoid, field lines run on this side south through the center to north. Okay? South to north on the inside of the solenoid, north to south on the outside of the solenoid. Now, how strong is the magnetic field in or around, inside or around the mouth, that's the hole of the solenoid? How strong is it? Well, we've got an equation for that. Of course, it's physics after all. Here is that equation. It's it looks complicated, but it's really not. This is magnetic field strength, beta. People do use the symbol B, but it's actually beta. Beta is equal to, this is called mu naught. It's a constant. It's a constant. It's just the ability of magnetic field lines to permeate through space. And you don't even have to worry about, remember its value or the units, because it's on the yellow sheet. It's down here, 4 pi times 10 to the negative 7, multiplied by n. N is the number of loops. The more loops you have in a solenoid, the stronger the magnetic field, times I, the current through those loops. The bigger the current you pass through a solenoid, the stronger the magnetic field will be. And then it's all divided by L. And that L is the length of the solenoid, because you can imagine, I could take, where's my piece of wire? I could take a loop like this, right? And it has just one loop. Or I can make smaller loops and a whole bunch of smaller loops with the same length of wire. I can make a whole bunch of smaller loops and compact them into a smaller area. The closer these loops are to one another, the stronger the magnetic field is going to be. Okay, so that's why the L is on the bottom. That's why it's divided by L. The length over which those loops are distributed. If I have a 30 centimeter long solenoid with 4 wraps on it, 1, 2, 3, 4, each of those loops are very distance apart. Whereas if I take those same 4 loops and I squish them together in 3 centimeters, 1, 2, 3, 4, they're practically on top of each other. The magnetic field that they will generate is going to be much larger. Okay, so magnetic field strength of a solenoid is given by this equation. How tightly packed are the loops, how much current through the loops, and how many loops the solenoid has determines the magnetic field produced by that solenoid. And that magnetic field will be the same everywhere inside the loop and around the mouths of the loop, the holes at the end. Outside of that area, it changes dramatically. It drops off quite quickly as you get away from the mouth or inside the solenoid. Okay? All right, so that's the lesson for today. We'll see you in lesson 3 next week.